Hello, my name is Miles Gapsinski. This is a recording for Project 3 of Software Development for Real-Time Systems at Johns Hopkins University. This project involves calculating the rotations per minute of a motor using an infrared emitter and detector pair and transmitting the RPM value over serial USB to a host machine. For this project, we had to use a round robin with interrupts or function queue scheduling architecture. I decided to use round robin with interrupts, and I configured the IR detector with a pull-up resistor to trigger an interrupt on a falling edge. You can see my IR detector here and my IR emitter here and the pull-up resistor that I just referred to. And the ISR for that IR detector increments a counter and flashes a red LED every time the propeller finishes blocking the IR signal. Here's the red LED that you'll see flashing on and off every time an ISR is triggered by the IR detector. And the main loop reads that counter value set by the ISR. It calculates an RPM value and outputs the RPM value over the serial USB to the host machine at a rate of 1 Hertz. As for the motor, the instructions had us building a Beekman motor, but I decided to use a DC motor instead. And this involved creating an additional circuit with a 9-volt battery supplying the power for the DC motor. You can see the battery here, and the power line and ground for the motor are here. And one hurdle with using a DC motor instead of the Beekman motor is that the DC motor constantly runs at full speed when it has power, while the Beekman motor increases its speed over time. Because of this, I had to figure out how to control the RPMs of the DC motor to mimic the behavior of the Beekman motor. So in order to control the DC motor, I decided to use a transistor, which acts as a switch that closes the DC motor circuit when the transistor receives power. You can see the transistor right here next to the LED status light. While reading through the Arduino projects book, I found that I also had to add a diode around the DC motor, which protects the Arduino circuit from back voltage generated by the DC motor. And that's a problem when you shut it off abruptly. And you'll see the diode is right here, and it's connected to the power, and it sits in between the ground and the power of the DC motor. And the black wire next to it right here is the ground of the DC motor up here. After I had that set up, I was able to turn the DC motor on and off, but I still needed to be able to control the DC motor's speed to mimic the Beekman motor. I found out that this can be done using pulse width modulation, which several of the Arduino Uno's digital pins are capable of doing. They're labeled PWM, and they have like a little tilde symbol next to them. Pulse width modulation mimics an analog signal by setting a pin's output value between high and low in intervals. This interval is dictated by the value written to that digital pin, and that's an 8-bit value, and so a value of 0 means the pin will never go high. 127 means the pin will be high 50% of the time, and a value of 255 means the pin will always be set to high. So after that, I was able to control the motor from software, but I wanted, instead of programming just a simple spin up and spin down thing that just repeats every time, I decided to add a potentiometer back here, which allowed me to control the PWM value and thus kind of ramp it up over time, but be able to dictate it myself. The ADC value, it's connected to an analog pin over here, so that's a 10-bit value that comes in, and since the pulse width modulation is an 8-bit value, I had to map the 10-bit value to an 8-bit value, and that value is read by the main loop at a rate of 10 Hertz. So in doing so, as I turn the potentiometer, you'll see in the demonstration that the DC motor will speed up, and if I turn it back down, the DC motor will slow down. So for this demonstration, I will begin by starting the board up without the motor running. I will then slowly increase the speed of the DC motor using the potentiometer I just talked about, and I'll do that until the DC motor is running at full speed. I'll have a putty window on the monitor which will read the RPM values of the DC motor every second. You obviously can't see that right now, so after some time into the demonstration, I will move the camera up so you can see Putty displaying the RPMs every second. Alright, so let's get started. Alright, I'm now going to connect to the board through Putty, and I'll show you the RPM output shortly after I get everything started. Just getting it set up on the monitor. So, as I alluded to earlier, I will use the potentiometer to control the speed of the DC motor. Just adjust it there so it doesn't hit. So this is going in about 12 revolutions per second right now, which is about 360 rotations per minute. I'm going to speed it up a little bit so you can see the light going a little bit faster. And that's now going at about 660 rotations per minute. And I'm going to increase it to about full speed. Just adjust that a little bit. So I'll now show the RPMs on the screen. I'm sorry. So you can see that it's going at about 1,530 or 1,560 RPMs. And now I'm gonna put this back up. And I'm gonna turn it back down. Now it's just about at the point where it's no longer going to work. And that thing comes loose a little bit, that's why I've been pushing on it. Alright. Oops, there it goes, fell off. Alright, thanks. That's it for the presentation.